Hi everyone. I'm gonna let this run for like 2 or 3 more minutes, let people come on in. Apologize for the delay. I had to change my stream settings because I was on Twitch last night, and that takes a second. So we'll get started soon. Yeah, I don't know what's going on with the announcements here. So I sent one out. I got a notification, but only from my blueprint. So now I'm just checking to see if it got sent to a different page. No, I totally see it on the course page. Why didn't you send an email, Canvas? Why would you not do the thing? That is super frustrating, but that's what we know and love Canvas for. So, hold on, let me send another announcement really quickly, and people will just funnel in. Oops. Because how many people are here right now? Oh, 16. So, almost everybody that gets the announcement is here anyway. So, let me just resend it anyway. Resending the last, not least, last announcement. Because it didn't go through for some reason to email. Okay, so delay posting, post at today, 2:08. Save. This is what I have to do every time I make an announcement. I have to delay the announcement. Oh, lovely. I posted it in the wrong thing. God damn it. I posted it in section A. Hold on. Delete. For some reason, it took me out of the blueprint. Because Canvas. I'm like, why can I not synchronize this? Let's see here. Because it didn't seem to email properly. Reset. There. Now I can post it to today at 2:08. Done. And then synchronize. Hopefully it works this time. Grumble, grumble. Okay. In a few minutes, that should go out and hopefully let people know. But most of you are already here, so that's fine. Okay, so let's see if I can answer questions here. Molar ratio of water to compound is just the unrounded molar ratio, right? Yes, that's correct. So before you round to a whole number, just report whatever numbers you get, and then in the next box below that, do the rounding. You should land very close to a number, like within 10%. Keep in mind, it is experimental data. So you will get a result that is close, but not quite super close, like the stuff in class that we've been doing. Let's see here. I think that might be all the questions. Everything else looks like a comment. Okay, so I'm on the wrong screen here. I gotta go over here. Excuse me, where's my pen? There it is. Alright, this is the last lecture. After today, it's all you. I will have nothing else to teach you. At least not for Chem 140. If you're coming to Chem 161, then I will have so many things to teach you. Oh my goodness. Speaking of which, make sure that you are doing enrollment because classes are filling. I think that there's quite a bit of space, though, so don't worry too much. Not just in my class, but I mean in general. What are we going to do today? We're going to learn how to dilute stuff. Yesterday... Oh, sweet. Good. I'm glad the email actually did what it was supposed to. You might get a second one. That might be the first one. Who knows? Yesterday, we learned how to create a solution using a solid reagent. So you pour some amount of solid into a flask, fill it with water, and then shake it 50 times and enjoy. Today, we're going to do the same process, except we're going to use a already made solution, and we're going to add water to dilute it. It said resent. Okay, cool. Thank you. So basically, we're going to take a solution with a high concentration. We're going to add some amount of that to a flask and then fill the remainder with water and then have a new diluted solution. This is really important in various applications such as being a lab tech and preparing solutions for people. We make super concentrated solutions, take tiny amounts of those, and then dilute them to huge amounts so that you have these dilute solutions to work with. Now, that's sort of my haha, very funny, it's important for you, isn't it, joke. But in reality, this is actually very useful for, like, preparing IV bags. If you ship IV bags across the country to everybody, you would have to ship a ton of water. But water is available locally. That's kind of silly. Why would you ship all of that mass around? So instead, what we ship around are either just the salt, the reagent that goes in it, or you just ship a really concentrated solution. Now, the concentrated solution might be prepared in-house and just kept in a stock room, and then you take a small amount of that when you go prepare the actual IV bags. That sort of procedure is basically what people follow in laboratories and also places like hospitals and stuff all over the place. So dilution is a very important skill to have, particularly if you're going into medicine. So again, the premise is we're going to take a concentrated solution, we're going to dilute it by adding water. I'm going to give you this formula specifically for dilutions. Now, it's very important to note that. So this formula is only for dilution. Now, why do I say that? Because in the next section, we're going to be working with molarity and volume. Yesterday, we worked with molarity and volume. You can work with molarity and volume all damn day. And then you see this formula and you're like, ooh, I want to use it. And it will ruin whatever problem you're working on if it is not specifically dilution. So be very careful. Whenever you write the dilution formula, think to yourself, dilution, dilution, dilution. Is this a dilution that I'm doing? Or am I doing some other reaction? If you're doing a reaction of any sort, don't use this formula. That's not a dilution. All right. To use this, we need to know what the parts mean. So S is the side for the stock solution. In other words, S is the solution you're starting with. This is the concentrated stuff. It's in the stockroom. You have tons of it. You only need a little. D is the diluted solution. And that's your goal. You want to end up with the solution. And you already know what M and V are. M is molarity, moles per liter, and V is volume. Now, very important here, in the previous iterations of molarity times volume, excuse me, we had to use liters because we wanted these units to cancel out, right? Because molarity is expressed in moles per liter, and we wanted this to happen. However, for this expression as written here, let's suppose that I wanted to solve for one of these, MD. So I'm going to rearrange my equation like this, MSVS over VD. And I decide that I want to put my volume unit in, let's be exotic here, cubic meters. Because I'm an engineer and I like to piss off chemists. Seriously, that's what they do. They piss off chemists. Well, fortunately, you and your engineering friends can get along great because whatever units you put in for volume are going to cancel out on both sides, so it doesn't matter. You're going to get a ratio. And that ratio is going to affect MS in the same way, whether it's cubic meters, square parsecs, or not square parsecs, cubic parsecs, or megaliters, or microliters, or whatever the hell you want to put in there. It doesn't matter. As long as the units are the same, they cancel out, and you get molarity at the end. So, for this formula, you can use any volume units you want, but the units have to match. That's the only requirement. So you too can piss off a chemist today. Congratulations. I've given you the keys. The rest is up to you. All right. Other than that, there are no real gimmicks to this formula, other than writing the formula down and then recognizing, oh, what part of this formula am I going to solve for? In almost all cases, you're going to be solving for VS, as you're going to see in the examples that we do. Written on the screen is just the text version of what I just said. So MS is concentration stock, MD is concentration dilute, VS is volume stock, and VD is volume dilute. Now, it helps us to understand how this process goes by looking at a picture. So let's draw a picture of what's going on here. So I want a solution. So here's my beaker, we'll say. And I'm going to say that this is, I don't know, 10 molar HCl. And from this, I want, we'll say 1 molar HCl. So I haven't made that yet, so it doesn't exist. And in order to do this, I'm going to take some amount, and it's going to go in here. Now, if I just took this volume, I would have 10 molar HCl, so obviously that's not the volume I want to take. But if I take some small amount, maybe 1/10, and added water the remainder of the way, that would be my 1 molar solution. So let's identify what the parts of our formula were. So this right here is the molarity of the stock solution. That's what I started with. This is the goal that I want. Now I'm going to make some amount of solution. So whatever volume of solution I wanted is going to be the volume of the diluted solution. And you might just think, oh, patterns, hey, I know where VS is going to be, and based on this pattern, that's not actually what you want to do. This right here is the volume of the stock that you use. Now, why does this equation work? And the answer is because if I do this, and I look at the units here, and we'll suppose that I put my units in liters here just to make this work out, so these units cancel out. And when I do this, I get moles before equals moles after. In other words, the number of moles that I took out of the stock solution will equal the number of moles of solute in the diluted solution. So whatever HCl was in my pipette that I grabbed from the solution initially, that's the only HCl that makes it over there. The rest I'm adding is water. And because the formula for molarity is moles over liters, if this number is constant, I can adjust the molarity up or down by changing these numbers. If I want the molarity to be lower, I make the volume bigger. If I want the molarity to be higher, I make the volume lower. So that's the theory behind this. All right, so let's do some numbers. Let's do some examples with numbers. There we go. So we're going to start with 10 molar calcium chloride. I want to make 3 liters of 0.5 molar calcium chloride. And so the question we're going to ask is, what the hell do we do with this? So first, let's identify the parts. I have this right here. This is going to be my stock room solution because it says that right here. And that's a concentration, so I'm going to call this MS. Then I have 2 parts down here. There's a volume and a molarity. Now, the keyword here, make, implies that this is the diluted solution I want to make. So this must be the volume of the diluted solution. And this must be the molarity of the diluted solution. Whenever you have a dilution problem, you're going to see words in the solution like this, and your job will be to pick them apart and figure out which one is which. Now, aside from contextual clues, there are also clues in the numbers. the stock solution is always going to be more concentrated. So the number that has the biggest value and also has the molarity units after it is MS. The smaller number with the molarity units must be MD, because that's what diluting is. You're trying to make a smaller concentration, right? So using those clues and the context of the problem, you should be able to determine what the numbers are so that you can then solve the calculation, which is the whole next step. Oops, nothing captured there. Let's move that guy. All right. Oop, what did I just do? Oh, I thought I closed PowerPoint. Not PowerPoint, but Photoshop. All right, so I'm going to start by writing down the formula. And then I'm going to write down the numbers that I know. So I have MS, and that is 10 moles per liter. This number didn't show up in our calculation, or not calculation, but in our problem yet. So I'm just going to do that for now. I know that the dilute concentration is 0.500 moles per liter. And I also know that the volume of that solution that we want to make is 3 liters. So, with that in mind, I must be solving for this thing. So let's do the algebra. I want to solve for this guy. So I'm going to take MS, I'm going to move him over there. And once I've done the algebra, I can just plug in all these numbers. So MD was 0.5. Make sure you bring the units along too. VD was 3.00 liters. And then MS was not 0. Let's undo. 10 moles per liter. Now we can cancel out units. Molarity and molarity just cancel. They're both moles per liter, so they would just cancel themselves. And the units that are going to be left over are liters, so I'm going to just punch it all into the calculator. 0.5 times 3 over 10. I hit the wrong thing. By hit, I wrote the wrong thing. All right, now that I have gotten that number, let's draw the picture that we drew before. So here's my stock solution. This is my 10 molar calcium chloride. I'm going to take some amount of it, and I'm going to put it into a container, or let's use a flask this time, with volume 3 liters. How much am I going to take? I'm going to take this much. So that's going to end up right here. There we go. The remainder of the solution will be, so this is this right here. The remainder here is water. And once you have done that, you will have created 3 liters of a 0.500 molar solution. So it looks just like the picture that we drew on the previous slide. However, I drew a volumetric flask because that's what we're going to be putting stuff into. Yeah, it looks like a bong, I know. That's what volumetric flasks look like. Now, you might be asked to describe this procedure in words or pictures, just like the previous examples where you made a solution with a solid reagent, and the process would be exactly the same. I don't have any space, so what we're going to do is we're going to do this. I'm just going to go whoop. And that's good enough for now because we're going to erase all this in a second anyway. So if you're asked to describe in words or pictures, you can do the same process. Step 1, oops, not add. We're going to take 0.150 liters of 10 molar calcium chloride and add it, that's supposed to be like an ampersand thing, to a 3-liter volumetric flask. So that was that first step. Put this stuff over here into this thing. After that, it's all the same process. Step 2, add water to the fill line. And then step 3, mix really well. And then, of course, enjoy. That's how you make a solution. So whether you have a solid reagent or a liquid reagent, you now know the procedure in which to make a desired solution. And it really comes down to just figuring out what quantity of stuff you need to put in there. When it's a solid, you need to figure out its mass. And when it's a liquid, you need to figure out its volume. So these slides go through that process. There's the visual of it too. The calculation at the bottom down here. Where's my cursor? There it is. This down here. That's just showing you that when you multiply the results on both sides of the equation, you get the same number of moles as a result. So what that means is that I took this many moles of calcium chloride out of the stock solution, and those are the only moles that remain even after dilution because I didn't add any more calcium chloride. The only thing I added by doing this process over here was water. All right, let's do an example. Let's suppose I have 14 molar HCl. I want to make 1 molar HCl because that's a nice round number, and I need a liter of it so that everybody in the class can use it. What do I do? So what I want you to do is tell me first the volume that you take from the stock solution to make this solution, and then do the 1, 2, 3. Step 1, do this. Step 2, do this. Step 3, do this, and type it all in the chat when you're done. Okay? So do the calculation, then write the procedure, and we'll go over the answer in about 2 or 3 minutes. See you in a bit. All right, let's go over the answer. I have too much empty space here. There we go. All right, so always start by misspelling the formula. There we go. Always start by writing down the formula. And then identifying the parts. So the stock solution concentration must be the bigger of the two concentrations. That'd be 14 moles per liter. That means that the molarity of the dilute solution must be the other one. Don't know the volume of the stock solution, but I know that the volume of the dilute solution is 1 liter. So we'll do the same calculation, and in fact, for almost every version of this problem, you're going to be solving for Vs. Now, that's not universally true. I could ask you different problems along the lines of, what would the volume be of a solution that was originally 2 moles per liter, but I diluted 10 mils of that solution to 0.8 moles per liter, or something like that. So you might have to solve for other things, but I don't remember which problem I wrote into Quiz 9. It does involve this formula. You might have to solve for something. What am I entering in here? MD, 1 mole per liter, 1 liter, 14 moles per liter. Molarity cancels out. You're going to get whatever 1 divided by 14 is. 0.71428. There we go. Now, let's suppose that I wanted that in milliliters, because that's an easier volume to work with. There you go. You don't need to put it in milliliters. You could leave it in liters. And then now that we've done that, we get to describe in words or pictures what we're going to do. We're going to take 71.4 milliliters of the stock solution and put it into a 1 liter volumetric flask. The volumetric flasks are the round ones that look like bongs. The reason that we use a volumetric flask is because their volume is very, very, very precise. So a beaker's really bad at volume, as we talked about way earlier in the quarter. But a volumetric flask is super, super precise. It is made specifically to hold that volume and no other volume. So you get more sig figs, basically. That's why I can say 1.00 liters instead of just 1. Step 2, once you've done that, add H2O to the fill line. Yeah, you can use whatever measuring implement you want, really. I'm not being super specific, but in the laboratory, you would specifically grab the flask that looks like this, and with a specific fill line that's like, hey, if you fill it to this line, that's 3 sig figs, or whatever. For our purposes, beaker is fine, but just know that in the laboratory, we won't really have beakers for you to measure stuff into, unless it's literally to hold a liquid. That's all beakers are good for. And then mix well. And then, of course, enjoy. Like, it's not your guys' fault that you have never seen a volumetric flask before, because I would have showed them to you in the lab, like, weeks ago. But we don't have labs, so what can you do? All right. I think that we get the gist of how to do dilutions. Just in case you wanted more practice. Oops. Here are 2 more problems that I'll leave up for you to do. Now, the first one is actually the, hey, surprise, you have to use the dilution formula but solve for something different. The second problem is the same as the problems that we've been doing so far, but I just wrote it a little bit differently, so don't let it fool you. So try these 2 problems. All I want you to do is answer the question. Don't write a solution prep for the second one. Just tell me what the answer is for each. So go ahead and try these. We'll go over the answers in just a second, and I'll be right back. One more minute to finish up these problems, and then we'll go over the answer. All right, let's try these two problems. All right, so the first problem, on first glance, looks very similar to the problems that we've been doing, but it is written a little bit differently. And so what it's asking us to do is, here's our beaker, and I have, oops, that didn't even make it over to the other side there. Oh, come on. There we go, that's good now. Here's my concentrated solution, and it is 15 molar. But then to that, what I'm going to do is I'm going to add enough water so that its new volume is something, but the concentration will then be 3 molar. And I want to figure out what this volume is. So the green stuff is the dilute solution, and the black stuff is the concentrated solution, or the stock solution. So when I go to my formula over here, we're actually going to solve for this volume right there. So I'm going to rearrange my expression to do that. And we'll plug in the numbers. So the stock solution molarity was 15 moles per liter. The volume was 0.2. And the molarity of the dilute was 3 liters. There it is. I couldn't find it on the screen. Or not 3. I messed up. Hold on. 3 moles per liter. Where is my cursor? There it is. So we have 15 divided by 3 is 5. 5 times 0.2 is 1.00. If the ending volume of my solution ends up being 1 liter, my solution will dilute and be 3 molar. All right, so that's problem number 1. That's the other type of problem you'll see here. Oh, I wish I could interact with this and just kind of scroll it down, but I guess I can't. All right. And this problem is exactly like what we've been doing before. So what volume of a stock solution, 6 molar, what volume should we use? Don't know. I want the volume of the dilute solution to be 525 liters, and I want its molarity to be 1.20. So we'll solve for this one. And we'll just plug in the numbers. 1.20 moles per liter. 0.525 liters divided by 6 moles per liter. Cross those molarity out. And I get 0.105 liters. So 105 milliliters is needed. All right. We're at 150, or it's 250 actually. So let's go ahead and take a break, because that's the end of this section, I believe, right? Yeah, let's do the last section after the break. And we'll talk about the lab, because this is the thing that we need to know to do the lab. So there's like 2 problems in here. Then we'll go do the lab. I'll walk you through it for an hour. And if we don't finish that, I'll make the remainder of a walkthrough on my own time for you. So let's do this. Let me turn on the timer here. Let me find the music. Where is my... There it is. Okay. All right. We'll see you in just a little bit. Oops, I'm sitting here answering questions and not looking at the timer. So to be more specific about your question there. Oh, I know, I was only off by the most I've been off all quarter. To answer your question there, um, hey, I got it exactly right yesterday, so I'm allowed to be off however much I want now. Ugh, now I have to stretch, hold on. So, when you do the heating process, there's a specific point at which you know that it's done, and when it is done, you put it in the desiccator. So it's not the desiccator that helps you figure out that it's done, it just keeps it that way. The reason being, the blue powder that they use in that experiment absorbs water vapor from the air, and it will actually just like gain mass by doing that. So I think the answer that I can say to your question that doesn't give away the answer is like it has something to do with mass. So be careful about like what they are doing with the crucible and the powder in it with regards to mass. All right, so let's see here. So this is the last section. We're going to talk about molarity and do stoichiometry problems with this, and then we're going to apply this to titrations. Now, I've actually looked over lab number 5. Lab number 5, we've already done the first half of it. So the first half of the lab number 5 was sections 16.3 and 16.4. How do you make a solution? You're going to have to make solutions for me in the lab, so that's going to be easy points. For this section, we're going to do some chemistry and do calculations with it. So what we're going to do here is we're going to use this information to do a reaction. And those reactions are going to be in the aqueous phase, and they're going to involve both molarity and volume. Because if you remember, and of course you remember because we just talked about this, molarity times volume equals moles, right? Well, remember that moles on our little chart can go any number of directions, right? So now we just have another way to get to that. And all that we're doing is the exact same concept. So here's our old chart. We're just going to stick these on the end here. And it's exactly the same thing that we did before, just using molarity and volume. If you're going through this transition here or this transition here, that's when you invoke molarity, because the conversion between volume and moles is molarity. So this is not a new concept, it's just a new way to approach this concept. So we're going to do 2 sample problems using molarity. And then we're going to go to the lab and talk about how to do the titration. Okay, so here's a sample titration. You could react sodium hydroxide with phosphoric acid and get these things. And you'll notice that this one is in the aqueous phase. This one's also in the aqueous phase, but it also comes as a solid that you put into water. So for this first problem, we're going to react aqueous sodium hydroxide with solid phosphoric acid. So the question asked is, what volume of 0.250 molar sodium hydroxide is needed to react completely with this? So I need to solve for a volume, and I'm given a mass to start. So I'm going to start here, and I'm going to end here. And so let's just take these calculations just like we would do any other stoichiometry problem that we did in unit, I want to say 14. Maybe 15. It all blends together for me. All right, so I have grams of phosphoric acid, and I want to figure out volume of, I could fix this. There we go. Volume of NaOH. So just like with everything, we're going to turn it into moles. And then I'm going to use the balanced chemical equation to turn moles of something into moles of something else. So let's do that. So I'm going to start with my mass of phosphoric acid. I'm going to change grams of phosphoric acid into moles. So that those cancel out. Then we'll turn moles of phosphoric acid into moles of sodium hydroxide. And then the last step, we want a volume, so I'm going to turn it into a volume. And if you're looking at that last one and thinking, oh, that looks like upside down molarity, then very good. That's what you want. Let's go and fill in all these numbers. So how do I get between grams and moles of phosphoric acid? I got to go find Lentech again. I don't have it up. Lentech. H3PO4. 98 moles per, or grams per mole. 98.00 per 1 mole. To do moles to moles, I use the chemical equation. There are 1 phosphoric acid per 3 sodium hydroxide. And then for this last one, this is just molarity. How many moles are there per liter of the solution that we have? Well, according to the statement, there are 0.250 moles per liter. And so I enter my numbers like that. Make sure you don't put the number on top, or otherwise that'd be 0.250 liters per mole. That's very different. All right, we punch it on the calculator. What do you get? 4.90 times 3 divided by 98 times 0.25. That's not the right number. So to do this titration, you would need 600 milliliters, which is actually a lot. But as you can see, this process that we are doing here is exactly the same as what we did with stoichiometry. It's just that now you have to put molarity in somewhere, and that somewhere is going to be the green circled region there when I turn from moles to volume. All right, let's do one more. Here's a different titration. I'm going to titrate calcium hydroxide with nitric acid. And this time, I want to know what volume of 0.125 molar calcium hydroxide would react completely with 15 milliliters of 0.225 molar nitric acid. So here I'm given a volume and a molarity of a starting thing. So I know how much volume I have, and I can get to moles of that using the molarity. I have a volume that I want to solve for at the end, and I know its molarity too, so I just have to go across this thing. So let's see how that shakes out for this problem. I'll just clear everything. All right, so I know volume of... I don't have the whole problem on the screen. There we go. I have volume of nitric acid And I want to solve for a volume of calcium hydroxide. I lost my arrows there. There we go. All right, same process, except in this case, I gave you a volume in milliliters. If you're ever given a volume in milliliters, you should turn it into liters right away. And then use that number to start with. So you could even just do this in your calculator and be like, oh, well, 15 milliliters is just this. So that's where I'm going to start my calculation. Or you could put all this in front of your calculation. That's fine too. So I'm going to turn volume into moles by going moles per liter. Moles of what? It's going to be nitric acid because that's what we're starting with. And then I can use the stoichiometry of the reaction to turn moles of nitric acid into moles of calcium hydroxide. And then I can turn moles of calcium hydroxide into a volume by using the molarity, just upside down. And that cancels out too. All right, let's punch in the numbers. What's the molarity of nitric acid? It is 0.225. What's the ratio of nitric acid to calcium hydroxide? There are 2 nitric acid per calcium hydroxide. And then finally, what's the molarity of calcium hydroxide? 0.0125 moles per liter. And I multiply that all together, and I get 0.1... Oops, that's not right. 0.0135 liters, or 13.5 milliliters. So if I were to put 15 milliliters of 0.225 molar nitric acid in a flask, I'd have to add 13.5 milliliters of this calcium hydroxide to totally neutralize it. And in fact, this is what we're going to do in lab number 5. So we're going to talk about that in just a second. But if you have any questions about these calculations, let me know, because this is the point of the second half of the lab, is to do this sort of calculation. All right, I'm going to put these on the screen, but we're not going to actually do this just yet. Because what we're going to do instead is I'm going to do a window capture, and I want to capture... Oh, it's minimized. So cancel. I can't find it because it was minimized. There we go. Let me make this smaller. Oh, you know, I don't need this part. Okay. All right, so this is lab number 5. Yeah, we're going to spend the rest of this time going over the lab. So if you've already done lab number 5, which is the new lab, this is due at the end of the, after finals, it's due. then you're all set. So part A is actually just asking you to do the stuff that we did earlier. So no problems there. But in part B, what you're going to be doing is you're going to be doing titrations. And in the titrations, you're going to have numbers that show this process where a burette is used to deliver a volume. And so what I want to do is I want to go over here. We don't need to capture that anymore. I want to capture that. That's too much. Okay. So what I'm going to do is I'm going to show you some data from the laboratory, and then we're going to show how this data was acquired. All right. So what is a titration? A titration is a very precise chemical reaction that is done using quantitative equipment. And so the equipment that's used is this really long, thin piece of glassware. You might have seen before. Ooh, it doesn't look like that, though. There we go. That's a little bit better. And at the end is a valve. And it holds a liquid. This is called a burette. And the way a burette counts is it counts like this. It goes 0, 1, 2, 3, and so on and so forth. It counts down. And so what that means is that when you spin this guy, the liquid falls out and the level decreases. The difference between the volume states at the end and the beginning is going to be equal to the volume used. So you can see on my chart there, I have initial reading of the burette, VI, and final burette reading, VF. What that means is I filled the burette all the way up, and it's full, quote unquote, at 0.20 milliliters. Then I opened the spigot, and I let it pour out, and when the reaction was done, the burette said 15.78. So what that must mean is that for trial 1 in this case, the volume used must be V final minus V initial. That's not V initial, that's V. There we go. So 0.20. Remember the rules for subtracting sig figs. We're going to go to this place, the hundredths place. There you go. That's step 1. So for trial 1, I used that volume. You do that for trial 2 and trial 3 as well. In fact, you need to in order to get the average volume. What I'm going to do is I'm going to assume that this was the volume that was used for this titration, as shown below. Now, there's a bunch of other numbers that are present on the screen there. So there is a volume of H2SO4 used and a molarity of H2SO4. So molarity H2SO4 and there you go. So you probably are seeing where this is going. I have a volume and a molarity, and I have another volume here. Could I solve for its molarity? Yes, you can. And that's the point. Now, how do you solve for molarity? We've only ever solved for volume using stoichiometry. Well, we'll show that in just a second. Now, for this specific reaction, the two reactants are these, H2SO4 and NaOH. And the procedure gives you an equation that you have to balance. And I'm going to assume that you can balance this on your own, so I'm just going to tell you the answer. So I need that, and I think that's it. No, I need this too. So now what we're going to do is we're going to use the number that we calculated up here, and we're going to use these numbers over here to figure out the molarity of the solution, which is what these directions are telling you. Calculate the molarity of the sodium hydroxide determined by each trial, then calculate the average molarity. So let's do that. So I know how much of this was used because I have the volume and the molarity right here. So if I take my volume in liters, just like before, we're just going to automatically turn it into the volume as liters. And I multiply by the concentration of the acid here. This will give me a number of moles of acid that are reacting. So in other words, in the flask that is reacting with the sodium hydroxide that I'm putting in here are this many moles of sulfuric acid. Then what I can do is I can say, okay, well, for every 1 mole of sulfuric acid, I have 2 moles of sodium hydroxide to react with it. So then I just do this. Okay. I'm going to turn moles of sulfuric acid into moles of sodium hydroxide. And according to the balanced chemical equation, for every 1 of those, I have 2 of those. So the number of moles of sodium hydroxide I have would be 376. And then finally, to get molarity out of this, well, what's the definition of molarity? It's moles of solute, which we just solved for, divided by liters of solution. Well, if I have this many moles of solute, how many liters were used to get that much? Well, if I go up here, I used this many liters, didn't I? So I'm just going to enter that down here. I've already forgotten the number. 1558. And that will give me a concentration in moles per liter. 0.00376, 0.01558. And there you go. That's how you do a titration. It's just like the problems we did on the practice. However, it's a little bit obscured. Like, we've hidden some of the stuff in different forms. So instead of saying, oh, it took 15.58 milliliters to react, I have hidden it into a before and after volume. But other than that, it's exactly the same. So think of the lab as practice problems for this section. Okay? You're going to do this 3 times. So I've done trial 1 for you. What I want you to do on the lab is I want you to do trial 2 and trial 3. And you should get numbers that are very similar to 0.241. The reason being is that the volumes that you are dispensing are also very close to the number that I got here. When you do this calculation, this right here and this right here will end up being constant because they depend on numbers that didn't change in the data table. I used 25 milliliters of sulfuric acid every time, and I had a solution concentration of 0.0750 moles per liter sulfuric acid. So those numbers all stay the same. But the volume changes each time. It depends on the experiment. And so you're going to get a little bit of variation in the concentration of sodium hydroxide. So in the lab guides you through this step by step. So calculate the number of moles of sulfuric acid. We did that. Then tell me the number of moles of sodium hydroxide you need to completely neutralize it. Then calculate the molarity and the average molarity. And then finally calculate a percent error if the target number was actually 0.2. You could do that. That's no problem. For the last part, I give you another chart, but you'll notice that the description has changed a little bit. For instance, there's nothing here. How the heck do you solve it then? And the answer to that is right here. So be very careful. You're going to take the answer that you got from this previous question, number 13, and you're going to use it for this problem, and you're going to go in the other direction. And so what that means is that you're going to say, okay, I have a volume of sodium hydroxide that was used. I know its molarity from question 13, so I know the number of moles of sodium hydroxide. I can then turn that into moles of vinegar, and I know with its volume I can get a molarity. So let's do an example of that too. Now, I'm actually realizing that I haven't actually illustrated the picture for you completely. Like, I drew the burette and I didn't draw anything else, so I apologize for that. Let me do this really quickly. So, in the burette, oops. That looks more like a necktie than a burette, but that's okay. So in the burette, we have sodium hydroxide. And you are pouring this into a flask. That's terrible. That's also bad. There we go. And the flask contains whatever you're titrating. So this is called the analyte. For the first experiment, this was H2SO4. For the second experiment, this is vinegar. Now we're going to write the reaction between sodium hydroxide and vinegar here. Sodium acetate and water. And that's actually already balanced. So for trial 1, for this one, we're going to figure out the volume. That's going to be 16 minus 9 is 5. 10, 9 minus 0 is 9. 17.95. All right. Make sure you're careful with sig figs. I did that 0.09 there for a reason, to see if you would end up with one sig fig forever. See if you know your subtraction rules, so be careful. So that's the volume of sulfuric acid. Or, I'm sorry. That's the volume of... We're not even doing sulfuric acid. That's the volume of sodium hydroxide used in the reaction. I'll do that. All right. Am I bad at subtraction? Yeah, I am. Thank you. I'm gonna have to call upon you guys again here, because what was the concentration of the of the sodium hydroxide from the previous problem? I've erased it. I want to say that it was this. 242. Thank you. I can do the calculation. Oh, you know, it's probably right in my calculator. Yeah, it's right there. Oh, I have 241. Oh, well, whatever. It doesn't matter. It's close enough. So with this volume and this molarity, I can figure out the number of moles of sodium hydroxide, which would then let me do moles of vinegar, which would then give me the molarity of the vinegar. Oh, is it the average? Okay, let's do 1 then. There we go. Just like before. We're just working in the other direction. If you know one thing, you can solve for the other thing. So the process we did here was we used known sodium, or I'm sorry, we used known sulfuric acid to solve for sodium hydroxide, and then we can use that sodium hydroxide to solve for any other unknown acid concentration. So let's do this. So I have this many liters of sodium hydroxide, and then I have liters, moles of NaOH. And we determined that that was... Oh, we'll fill in those numbers later, actually. All right, so I'm stopping the calculation here because then we're going to take this result and divide by the volume used, which is currently cut off on the thing. That does say 1797. Can I do that? There we go. Yeah. Sorry, those numbers kind of got glued together there. My pen didn't quite leave the canvas. All right, this concentration is of our base. It goes right here. And then according to the balanced chemical equation, there's 1 sodium hydroxide per vinegar. So in this reaction, I got 0.00433 moles of vinegar. So that's this number here. Then to get to molarity, remember that molarity is just moles of solute over liters of solution. So I'm just going to take that number up there and divide by what volume of it I used. Well, unfortunately, my data table doesn't show that. I have to scroll it down a little bit. We use 25 milliliters, so I'm going to turn that into liters. And that's also a 1.7. 0.173 moles of vinegar per liter. So that's the molarity from trial 1. You should get a very similar result for trials 2 and 3. And that's more or less the lab. There is a last question, number 21, that is basically a practice problem that we've done in class, which I'm showing on the screen here. And you can totally do 21 now. In fact, you do the entire lab. Now, this is intended to be practice for the final. There's maybe one question of this nature on exam 2. I think I did one titration problem. But it looks more like this problem that you're seeing on the screen in the blue PowerPoint slide. It's simpler. It's not obscured by titration data, etc. Do you want to use the average? Yeah, I'm just showing you how to do the calculation with the number that you gave me. If you use the average calculation, it would change very slightly. Where does the answer go? You're going to put that in the Google Sheet for lab number 5, which I haven't brought up yet. But we'll show it here. Oh, I got to go to the Canvas page to get that. Not my Google Drive, because that'll just take forever. So remember that, like for all labs, there's a Google Sheet. I tried to click on it, and it took me to the Unit 1 slides, because Canvas. Come on, Canvas. I don't have all day. All right, if I window capture, not that, but the lab sheet. There you go. So lab sheet number 5 has a lot more stuff that you're going to be filling in. So here's the data table that you saw. And then my worksheet asks you, calculate the number of moles of sulfuric acid. So we already did that, all of these for trial 1. Then once you've done this for trials 2 and 3, you just take the average of these numbers and report it. Okay, so let me go back. So where would we put the 0.173 molar on the lab? Okay, so that would be down here when we're doing vinegar. The result that I would have got for trial 1 would be right here. And then for Meg's question, let's see here. So the average sodium hydroxide volume is asked for, but you don't have to fill it in for that problem. So like all these numbers, you could fill them in however you want to. But I'm not actually grading those because that's not the objective of the problem. Oh, I got to clear this too, because otherwise you're just going to keep my numbers. So the number you entered in the Google Sheet will be different for trial 1. So for trial 1, when we did this, so you would subtract these two and write that here. There you go. And then whatever these numbers are, and then you would take the average and write the average here. So whatever the average is goes there. But what I want you to do is I want you to complete the calculations using each trial. So you aren't going to actually use the average NaOH volume. You're going to use this number to get this number, and then this number to get this number, and then this number to get this number. I think the problem that's coming up is this number right here, the average sodium hydroxide volume. Like, it looks like it's important, but I'm not having you use it for anything. The molarity you are using, where'd you get this number? That would be, oh, that would be this number here. So once you have done all 3 trials for question 13, you're going to then take the average. And then you're going to use that number, and that number goes here. The reason that you're going to take the average at that point is because that's just how I've set up the worksheet. That's really the best reason I have. You could have taken the average volume and then done the titration calculation with that once. I think the reason that I made you do it this way 3 times is for practice. Because I'm looking at this and I'm like, you don't have to do that. You're going to get the same error anyway because you're multiplying. I see, okay. Yeah, because you, so this is what happened then. So you got that, oops. And so that's what your worksheet says then. You're going to use this number for that, oops, that didn't work. You're going to take this number and use it for that calculation continuing. I use the different number because that's the number you just told me. Or, I don't know what happened. This is the number I used. It doesn't matter. This is for practice. When you do it, you're going to use this number. And I apologize for that confusion. Now I got to undo everything I did. There we go. I think that's good. Otherwise, the worksheet's going to have all these numbers filled in. All right. Cool. We're on the same page now. No, it's good. Sorry, I apologize for that being confusing. For number 11, each trial is 0.00188. I believe it should be, yeah. So you're going to get the same number for these and also for these. So 11 and 12, they're all going to be the same answer. Because those depend on these numbers, which are constant. All right. There is one last thing I want to talk about for the lab. And so I do realize that everybody is going to be studying their asses off for the final and for the exam too. And they're not going to have much time. So this lab is still for credit, so it's going to be worth some points. But what it's going to be worth is instead of 25 points, I'm going to make it... What did I write down that I was going to make this? Sorry, I had this all worked out. I'm trying to find it in my notes now. I have this engineering pad that I've written like 75 pages of just me doing problems for this class. And, of course, I can't find it. Okay. So this lab is due Friday next week, which is the 11th. Okay. And that's a hard deadline. So I cannot NQA this past that deadline. Everything for this class is due by then. If you don't get it to me on that day, I won't be able to grade it because grades will already have been submitted. Okay? Now, the other things that I'm going to do for this is I'm going to make the lab, it's not going to be worth 25, because if you just have no time, then, like, I don't want to penalize you 25 points. So what I'm going to do is I'm going to make it worth 15 points. And all I'm going to do is just to check to see if you did it. Okay? So if you attempt the lab, and what that means is that you put numbers in, I'm not going to check for sig figs, I'm going to check that your answers are relatively close to the correct answer, and that you typed in something reasonable for the problems at the end. Well, I'm trying to find this. There we go. So when you get down here to this stuff, that you have written something and then you tried to explain it. Okay? If you did that, and these have like descriptions in them that are reasonable, if you do that, I will just give you 15. Okay? So your grades are going to be either 15 points or whatever percentage of the assignment you did. So if you left half of it blank, you'll get half of 15. Okay? Don't leave it blank. That's really the thing that I'm trying to get you to do for this experiment is don't leave it blank. Try to do the assignment. Do it with a friend. Work together. I'm not going to check for plagiarism on this one because I realize that you're going to be working really quickly. So if you have the same exact wording as somebody else, I'm going to assume that you work together. Don't just copy off of somebody, obviously, because you're not going to learn. But I'm not going to go through this with a fine-tooth comb like I do for the other labs, because you're going to turn it in on Friday, and grades are due within a day or two. So I have to grade them really quickly. But also, because you are stressed out about it being the end of the quarter, I want to make this rather low stakes. As long as you try to do it, you'll get 15. Okay? All right. That's pretty much it. So, I mean, I have 10 more minutes in class, but I really like to go to the bathroom. So, what I'm going to do is I'm going to leave this problem on the board for you to do. I'm going to go quickly use the restroom, and when I come back, we'll go over this answer, and then we'll celebrate, because that's the end. It's right there. So, oh, I forgot I had the audio there, so you got to hear a little preview of the celebration. So do these last two problems. We'll go over the answers in just a second. Otherwise, I have to put it on an announcement, because someone will email me about it. We'll do this on the video. I'll be right back. I'm going to run out of time if I don't do these problems, so let's do them now. Oh. Gotta get rid of that. All right. Let's clear this off the screen. All right, so the first one is... What is this that I've selected? Oh, that's window capture 5. I don't care about that. Let's just lock that. So I stopped clicking on it, that's why. So the first problem is like a titration. So we got iron 3 hydroxide, 52 grams of it. So we've got a mass of iron 3 hydroxide. And I want to find out the volume of HCl. So if I turn this into moles, and this into moles, I can then turn one into the other. I tilted the board again. There we go. All right, so we're going to go grams of iron 3 hydroxide, moles. So those cancel. And then we'll go moles of iron 3 hydroxide to moles HCl. So those cancel. And then moles HCl and volume HCl. All right, we fill in the numbers. I got to go to Lentech one last time. I didn't close Lentech, did I? I did not. Okay. Fe parentheses OH parentheses 3. That's not... There we go. I forgot the number. 106.87. It's in green, apparently. That's fine. And then how many moles of iron 3 hydroxide? 1 per every 3 moles of HCl. And then what's the molarity of HCl? 1.50 moles per liter. So I'm going to do that calculation and get a volume. And I get 52 times 1 times 3 times 1 divided by 106.87 times 1 times 1.5. And I got 973 milliliters, or that many liters of 1.50 molar HCl. You don't actually need to write the of 0.150 molar HCl part. I'm just doing that for clarification so that you can see it. And that should make sense. Like, oh, yeah, that's the acid that we turned it into at the end for our calculation. And then finally, how much FeCl3 will be made? Well, this whole part right here, this is the power of Photoshop. I can just take this and go... Oops, that's color balance, whatever the hell that is. There we go. Because that part of the problem doesn't change, right? It's just instead of going from moles of FeOH to HCl, we're going to go to moles of FeCl3. And then how much are we making? I didn't tell you which unit, but hopefully you assumed that it was in grams because it is. So that cancels out with that. And then we can just set up the stoichiometry problem just like we would have in the previous chapter. I'm sure this is 1-to-1. I don't know what the FeCl3, 162.2. (52 times 1 times 1 times 162.20) divided by parentheses 106.87 times 1 times 1. 78.9 grams of FeCl3. That's it. That's me throwing my pen on the pad. It's over. There's nothing left for me to do. The rest is up to you. But for now, you get to celebrate. Oops, I had this muted. Hold on. You get to celebrate. I said celebrate, damn it. Hooray! Oh, my music cut off there because I touched the pad. And I didn't even circle the right part because I wasn't prepared for this part. You have completed Chem 140. Yeah, you can use the answer from that because they're all interconnected. So you could start from there and then work towards the answer. Either way works. And that's it. No more lectures, no more slides, no more nothing. The rest is up to you. Tomorrow there will be a review session from 2 to 4. And on Monday is exam number 2, which will cover units 9 through 16. Can I write on this slide? Am I allowed to draw all over this? No, I can't. It won't let me. So, I mean, I guess it's just everything that's down at the bottom. So, exam number 2 is on Monday. It'll be open all day. Make sure that you complete the exam during that time. If for some reason you are absolutely unable to do so, email me immediately. If you have like a doctor appointment or something that's going to take up the whole day, please, you gotta let me know. Okay. All right. Once exam number 2 is behind us, there will be a review session on Tuesday and Wednesday next week for the final. It'll be the same time as the normal class periods. I will just be there to do worksheet problems of any type that you want. Answer any questions you might have on Tuesday and Wednesday, and then we'll just go until people stop asking questions. And then on Thursday is the final exam, which is at unit everything. All right. That's all I got. Thanks for coming out to the last lecture, and thanks for being a part of Chem 140 this week. You guys may make it worth it. For all of the crap that everybody has to deal with the pandemic, it's nice to have this little constant thing that I can come and see people, and even though I don't know who the hell you are, I recognize names, and seeing people's names repeatedly is comforting. And that's kind of what I dig about being a teacher, is I get to see people, and hopefully I made a difference and impacted you in some meaningful way. Best of luck, and we'll see you again in 161. Awkward pause. Where's my outro? There it is.